Hello students, in this session we are going to study overhang beam with uniformly distributed load. So let us have a beam which is overhang and carrying a UDL. Suppose this is our beam and it is carrying UDL like this, and suppose it is overhanging that the supports are at the inner part of this beam and the length is, this length is L, the length of the beam is L between the supports, length of the beam is L between the supports, and this overhang part has equal length of A, this is A, as well as this is A. The overhang part has length of A, right? So L, A and A, and the intensity of load is W kilonewton per meter. Suppose the intensity of load is W kilonewton per meter. So this is given to us, right? So intensity of load is given to us. The L length between the supports is given to us, and the A is the overhang part of this beam. This is given to us, and we have to draw the shear force and bending moment diagram for this beam. Shear force and bending moment diagram for overhang beam which is carrying a UDL, uniformly distributed load, right? So now you can see here a symmetry that the load between the supports and overhang is all equal. So there will be reaction at these 2 points. Suppose this is A point, this is B, this is C and this is D. So there will be reaction at B point, which is RB and RC. First we have to find out RB and RC, and then we will be able to find out the shear force diagram. So what is RB and what is RC? You can see here there is symmetry. It means that the reactions will be equal, right? Equal load will be taken by point B and equal load will be taken by the joint C. So you can see from the symmetry RB will be equal to RC. RB will be equal to RC. And what is the total load? Total load, vertically downward load. So the total load is W multiplied by the length. You know that for rectangular section we have already told you that the UDL is like a brick, like a rectangular brick placed on a surface. So rectangular brick has total load of length multiplied by the width. So this is W multiplied by the total length, it is L plus 2A. So W multiplied by L plus 2A is the total weight acting at the center. So it will be acting at the center here. So total load which will be acting at the center will be equal to, this will be equal to W multiplied by L plus 2A. So this is the total load. This is the total load acting, and out of this load half will be shared by B and half will be shared by C. So RB will be equal to half of the total load applied due to symmetry. So W L plus 2A by 2, this is our reaction at point B, and RC, this is equal to W L plus 2A by 2, this is a reaction at point C. So we have obtained the reaction at point B and C. Now we want to find out the shear force. We have obtained the reactions, now we want to find out the shear forces. So as usual we will take the cross section at a distance x from the free end. So I am taking here the x cross section at a distance of x, small x from the free end A, right? And what is this load? What is this load? This load is, this much load is W multiplied by the distance Wx, which will be acting at x by 2 of the x, right? So this distance will be x by 2. So this Wx will be acting at x by 2 from the capital X, right? So what is Fx? Fx, and this will be valid between A to B because there is a reaction at RB. So we have to take another section between B and C and another section between C and D, right? So we are taking here only A to B section, A to B length, this length of the beam, right? So shear force Fx will be equal to, that will be equal to, what is shear force? This is the sum of all the forces to the left or to the right of the section. It is easy to take the left of the section. So to this cross section X, to the left of this section, the force is Wx. So we are taking Wx, right? And according to sign convention, if the force is on left downward, this is negative. So this should be negative Wx. So this is minus Wx. So shear force is varying linearly between A to B, right? And it is valid between A to B only. So this is a shear force. And we can find out the forces at the endpoints at A and B using this equation. So what will be Fa? What will be Fa? That will be equal to, put x is equal to 0 because at A x is 0. So this will be equal to 0 because x equal to 0. And what is Fb? That will be equal to, put the value here, x is Fb and x will become A. So you put here A, so this will be minus Wa and x will be here A. So this is Fa and Fb. From 0 to minus Wa it is varying and in a linear fashion, minus Wx, linear fashion. So we can draw shear force diagram now very easily. So draw the shear force diagram between this. So you will get, so this is our, suppose, beam. This is A point, B point, C point and D point. This is 0. This is 0 at A point, minus Wa at B point. So suppose this is minus Wa, this much is the minus Wa, and draw a straight line in negative direction like this, right? So this is minus Wa and this is negative. So this is the shear force diagram between A and B. Now we want to find out between B and C. This is valid between A and B. Now we want to find out the shear force between B and C. So I'm separating this from the previous one. What will be the shear force between B and C? We have to take another section at a distance something. So let us take another cross section x1 at a distance of x1 from the free end, small x1 from the free end. So from the free end A, we have taken a cross section x1 at a distance small x1 from the free end A, right? And what are the forces? What are the forces acting to left of this section? To the left of this section. One of the force will be the weight of this UDL up to Wx1. So this part will be added in between. This part is the extra part which will be added. So from A to C, this is x1, right? And the width is W, which is the weight. So W multiplied by x1 will the load acting downward, and another is RB. So there are two forces. Basically there are two forces. I can make it here for better understanding. This is our UDL. This is the UDL, and this is suppose we have taken here, and this is downward. This distance is x1. This distance is x1, and the UDL is acting downward like this. So there will be a central load acting on this. The width is W. So Wx1 will be acting downward. Wx1. and one is the normal reaction, reaction of this, that is RB, right? So this is the case. So to left of this section, to the left of this section, this is our x1, this section x1. To the left of this section, there are two forces basically. There are two forces. One is Wx1 and another is RB. Wx1 and RB, right? So force on x1 will be equal to, force on f1 will equal to, this is downward negative to the left. We are checking on the left of this section. To the left of this section, if this is downward, this is negative. So this is minus Wx1 plus RB. RB, what is RB? RB is WL plus 2, L plus 2A divided by 2. This is positive, minus Wx1. So this is the shear force. This is the shear force at the left of x1. Now you are able to understand that, right? So next is, we can find out between B and C. Between B and C, what will be the variation of shear force? So what is the shear force at B? FB. Shear force FB. At shear force FB, the x1 will become A. X1 will become A. So put the value here, WA, WL. So this will be WL by 2, because put the value here in this equation, and this x1 will be equal to A at point B, right? So the value will be WL by 2. WL by 2. This is our FB when x1 becomes A. And what is FC? What is FC? Because this is valid. This is valid between B to C. This is valid between B to C. This was our A point, and this was our B point, where normal reaction RB is acting, right? So A point was this, B point was this, x1 is this. We are taking load in this direction. We are checking the loads, forces. So FC, about FC, the distance become L plus A. L plus A. Put the value L plus A here. You will get W L plus 2A divided by 2 minus W. Thus at C point, the distance become L plus A. So this is L plus A. And this will come out to be, solve it, and you will get the value, the FC. You will get, what is the value of FC? That will be minus WL by 2. Solve it and you will get minus WL by 2. This is at when x1 becomes L plus A. When x1 becomes L plus A, right? So this is the case between B and C. So now we are able to draw the shear force diagram between B and C using this equation, between B and C. So what is shear force diagram between B and C? How can we find out? At B, there is abrupt change. There is abrupt change from minus WA to plus WL by 2. There is abrupt change. So to the just left of this B, there is just left of this B, there is the shear force is WA, minus WA, and just to the right of B, the shear force is WL by 2. So there is abrupt change. So this is from minus WA to WL by 2. So this part is WL by 2. So minus WA to the abrupt change, this is WL by 2. And then at C point again, the force is minus WL by 2. Shear force is minus WL by 2 in negative direction. So this is in negative direction, like this, right? And there is symmetry. So this will pass from the center. So passing through the center, you will get this type of line, right? So this is positive part and this is a negative part, and this is a straight line, because this is a straight line here. You can see here x1 is a straight line, variable is x1, and this is a straight line equation, right? So this is WL by 2. WL by 2, right? So we have drawn the shear force between B and C, and this is center, right? This is center, and you know that where the shear force is 0, bending moment will be maximum. So at this point, bending moment will be maximum when we draw the bending moment diagram. Now further, between C and D, what is happening between C and D? What we can take is, it is better to take the cross section to the right of this section, right? And at x, suppose x2 we are taking, and take a distance small x2 from the free end. Now variable is small x2, and the weight will be acting in downward direction, and that will be wx2. So wx2 is the weight acting in downward direction. So rightward downward is taken as positive. So this is a positive force for this case, right? Because we are seeing in rightward direction of the x2, right of the x2. We are seeing in right of the x2. So here we can make this small figure. I am making here for more clarity. I am making here. This is a small x2 distance. And the force is, weight is downward, and the center of this will be acting at the center of this brick, that is wx2, and this is point D, and this is the x2 point, x2 cross section. This is this, right? And we have to take the forces to the right of the section if we want to find out the shear force. So what is the shear force at x2? So shear force at x2 will be equal to sum of the forces to the right of the section, and there is only one force, wx2, and wx2 is positive. To the right of the section, if the downward, there is positive, so it is wx2, right? And then there are 2 points, and it is valid between C to D. Then what is the force at the peak points like FC? At FC, x will be A, x2 will be A. So you can put here A, you will get WA. Right? So this is because x2 is now A. And what is FD? That is equal to 0, because x2 is 0, because we are taking x2 from that point, D point, to in this side, towards my side, right? So this is the shear force between C and D. Now we can draw. This is a straight line, and FC is WA positive. So FC is WA positive. So WA positive, you can take here, this is WA positive, this is WA. So there is abrupt change. To the left of the section, the force is WL by 2. To the just right of the C, the force is WA. And FD is 0, and there is a straight line between them. So FD is 0, and there is a straight line between them, this line, right? And this is positive. So this is the shear force diagram for this beam, overhang beam with UDL, right? First, it is 0 at point A, it is minus WA at point B, then there is abrupt change. At the left this is WA, at the right this is WL by 2. There is abrupt change, and then there is linear variation till at C point the force is WL by 2. You can see here FC WL by 2 minus, right? And then again there is abrupt change at FC, this is WA, so this is WA positive, and then FD is 0, and linear variation is there. So linear variation is there. So this is how shear force diagram is drawn for overhang beam with UDL. Now we want to draw the bending moment diagram for the same. Bending moment diagram, right? Let us draw now the bending moment diagram for the same beam. We are utilizing the same cross sections. First of all, take this cross section and find out the bending moment at cross section X. bending moment at cross section X. Let us draw the bending moment, right? So first, between A and B, take the cross section. This is X at a distance X from the free end A, and then find out the moment of this force about X. So we have taken this part AX. I am making here AX part here, small part AX, this, right? And this is in downward direction. The weight is W, width is W, and this is our X, and this is A to X, right? This part AX, and the length is X, small x is the length. The weight will be acting downward at the center WX, which is at a distance of x by 2 from the capital X. So this distance is x by 2 because it is at the center of this, right? So this is the case, right? And we have to take the moment of all the forces to find out the bending moment of all the forces to the left or right of the section. We are taking left of the section. So mx will be equal to the moment of this, and this is anti-clockwise to the left is negative, right? So this is hogging bending moment, anti-clockwise left is negative. So this is minus wx multiplied by x by 2. So this is wx square by 2. So this is the bending moment wx square by 2, right? And it is valid between A to B, Then what is bending moment at A? At A, x is 0. So you will put MA is equal to 0 because x is 0 here. And what is bending moment at B point? That is equal to minus W A square by 2 because x is A here. X will become A. So this is the bending moment at A and at B, and this is the variable, and this is parabolic variation. The variation is parabolic variation, and it is in negative side, right? So now we can draw the bending moment between A to B. So by this you can draw like this. This is A point, B point, C and D. From MA 0, at M A point this is 0, at B point this is WA square by 2 negative. So this is WA square by 2 negative. Suppose that is this point. This much amount is WA square by 2 in negative direction, and it is parabolic. You can see here WX square by 2, it is parabolic, right? So it is a curvature here. You will get a curvature like this here. So by this we have drawn the bending moment between A and B. This is valid between A and B. So we have drawn that, right? Now we have to draw the bending moment between B and C. What is bending moment? So draw that between B and C. And you know that the shear force is 0 at this point. It means bending moment will be maximum at this point. So here you will get some maximum bending moment at the center of the beam, right? So draw. First you can take a section. We have taken the section x1 at a distance of x1 from the free end. So we have taken a small section x1. Why we are taking? Because this is force is changing here. RB is coming into picture. That's why we are taking for B and C a separate section, right? So the UDL is acting in downward direction. This is A point and this is X point. A to X1 point, and this distance is X1. This distance is X1. So this is X1 from A to X1. And the force of this brick will be acting in downward direction at the center. Just at the center, right? And what is the amount of this force? That is W multiplied by x1, W x1. And this Wx1 will be at a distance of x1 by 2 from the center. And there is another force RB. There is another force RB here, right? So this is x1 by 2 and there is another force RB here, right? RB. So there are two forces, Wx1 and RB, and we have to take the moment of both the forces, Wx1 as well as RB. And Wx1 is negative because it is anti-clockwise on the left, and RB will be positive moment because it is clockwise at the left, right? So, and what is the distance of Wx1 from x1? This is x1 by 2. And what is the distance of RB from x1? RB from x1 is will be x1 minus a. So this distance will be x1 minus a, right? So we can find out the moment of x1, that will be equal to RB is positive, so RB multiplied by x1 minus a. What is RB? This W L plus 2a by 2 multiplied by this distance, perpendicular distance between RB and x1. This is x1 minus a. x1 minus a. So this is the moment of RB. And what is the moment of Wx1? And this is negative according to sign convention. This is negative. Wx1 multiplied by x1 by 2. So this will become Wx1 x1 square by 2. So this is the bending moment. This is the bending moment at point x1, which is valid between, and this is valid between B and C, between these 2 points, B and C, right? So this is valid between B and C. B to C, it is valid. I am writing here B to C, it is valid, because we have taken cross section between B to C. Then what is bending moment at B? What is then bending moment at B? And what is the value of x1 at B? At B, the value of x1 is a. Value of x1 is a. So put here a, x1 a, x1 a. You will get the value x1 a minus a will become 0. You will get minus w a square by 2. So you will get minus w a square by 2 when x1 is a. And what is MC? MC, that will be equal to, MC will be equal to, at C point the distance become L plus A, L plus A. So put here x1 equal to L plus A, and what value you will get? Check the value you will get. Put x1 is equal to L plus A here, and by putting x1 is equal to L plus A, you will get the same value, minus w a square by 2, minus w a square by 2 when you are putting x1 is equal to L plus A. This A plus L, so this is the distance, x1 is equal to L plus A. So you have found out MB, you have found out MC using this equation, right? And this is minus w a square by 2 and minus w a square by 2, and it is a parabolic curve, it is a parabolic curve, and because we know that at the center the shear force is 0, there will be a maxima at this point. So what type of curve you will get? The curve you will get will be like this. This is w a square by 2. Again at C point you are getting the same result, and but there is a maximum, there is a maxima at this point. So you will get this type of curve, parabolic curve for this, right? This type of parabolic curve where you are getting maxima at this point, right? This is our E point, maxima is at E point, isn't it? So this is how you can get the value of these quantities, bending moment, right? And further, what is the movement between C and D? How the variation is there between C and D? So between C and D, how you will find out between C and D? And one more thing, that what is this maximum bending moment? What is the value of this maximum bending moment? This value. If this is m max, what is this value? For this value, because it is at the center, so put x1 will be equal to, this is a plus l by 2. Put x1 is equal to a plus l by 2, you will get the maximum value. So for maxima, for m max, because m max is lying at the center and center is a plus l by 2, a plus l by 2. So for m max, put x1 is equal to a plus l by 2. This value put in this equation. Suppose this is equation number, this was equation number 1, this is equation number 2, suppose. In equation number 2. So in this equation, put the value x1 is equal to a plus l by 2, you will get the maximum bending moment. So solve it and you will get, I am writing it at center. Rather than writing max, this is, I am writing m at center. Center, whatever is the maximum bending moment, this is at the center, right? M center. So I am writing it as a m center. At center point, what is the bending moment? M center. So put x1 is equal to a plus l by 2 and you will get the bending moment at point E, at the center of the beam. What value you will get? W by 2 L square by 4 minus A square. This value you will get when you put here x1 is equal to a plus l by 2. So this is the maximum bending moment. The bending moment at the center. This value you will get, right? You can say it as a maximum, or you can see the value at the center, right? So this value is basically how much? W by 2 L square by 4 minus A square. So this is the value at the center. By putting x1 is equal to a plus l by 2, the value at the center, a plus l by 2, right? So you will get this equation. So you have got the maximum value, or the value at the center. Now what is the bending moment diagram between D and C? D and C, right? So I am doing here between D and C. So what will be happening between D and C? So between D and C, you will take this section from the free end, take a cross section x2 at a distance of x2 from the D. So I have taken a small cross section, this type of cross section at center. Distance is x2, this distance is x2, and the weight is wx2, and this is our cross section x2, and this is D point, right? And we have to take the moment of this wx2, and what will be this distance? This distance will be x2 by 2, because it is at the center of this prick, x2 by 2, right? So mx2 will be equal to how much it will be? This is the moment of this wx2 at x2, right? And this is clockwise at the right. Clockwise at the right is negative, so it will be minus. So minus, and how much it will come? This will come out to be this value only. So w x2 square by 2, and this is a value between D to C, right? So what is MD then? MD, this is 0 because x2 is 0, and what is MC then? That is equal to minus WA square by 2, because x2 is a, that's it. So put the value, this value, you will get minus WA square by 2, this is 0, you will get the curve like this, similar curve like this, right? You will get this. So this is how the bending moment diagram of this beam, overhang beam with UDL, is drawn, right? So this distance is WA square by 2, right? So this distance is, here I am writing this distance, this is WA square by 2, right? So this is the bending moment diagram. So this is bending moment diagram, and this was the shear force diagram. So this is how shear force diagram and bending moment diagram is drawn for a overhang beam with UDL. Now in this diagram, overhang beam with UDL, we want to add something. We have already drawn the bending moment diagram for this case, overhang beam with UDL, right? And we have found out that the moment at the center is, bending moment at the center is W by 2 L square by 4 minus A square. This was the bending moment at the center, this value at the center, right? And this value was A, this is L, this is A. And we have found out the bending moment diagram like this, right? But you can see here the bending moment at the center also depend on the comparative term of A and L by 2, right? If A is less, if A is less, this term is positive, more positive. And if A is more, if overhang is more, this ME will become shrink and it will become lower, right? And there may be case at certain point where this A square and L square by 4 will become equal. So we can have three cases. One is this case where A is less than L by 2. Where A is less than L by 2. If A is less than L by 2, then it is okay. This is the diagram, right? A is less than L by 2. We are getting this curve. So this curve is basically for, this bending moment diagram is for A less than L by 2. But what will happen if A will become equal to L by 2? Then what is going to happen? When A becomes equal to L by 2. So then in that case, you will get this type of curve. This is always there. This is always there. These two curves, right? So this is A, B, C, D, right? So second case, if A equal to L by 2, in that case, in this case, ME will be positive. In this case, the bending moment at the center will be equal to 0. At the center will be equal to 0 because this term will become 0, right? So ME will become 0. So our curve will be changed like this. This will be the curve. And E point, the bending moment is 0. So this will be the curve. Third case is when A is greater than L by 2. Third case is A is greater than L by 2. You can see here in this equation, A is greater than L by 2. It shows that the ME will become negative because A is greater than L by 2, right? So A square quantity will become higher than L square by 4. So this shows that the bending moment at E point will be equal to negative, right? So if we draw it, you will get, this is our beam A, B, C, D, and this is the center E, and this will curve, this will be always be there, this parabolic curve, and then the bending moment will remain negative at point E. That is, the curve will be like this, There is some negative bending moment at the center, right? So this is that negative bending moment at the center. So this is ME, which is negative in this case, right? So this is ME. and which is negative in this case, right? And in this case it is 0, ME is 0, and in this case ME is positive, right? So by this you can find out the bending moment at certain points, as well as you can draw the bending moment diagram. So by this you can draw the bending moment diagram for any case of overhang beam with UDL. Overhang beam with UDL. Now let us proceed further. In this case, in first case, let us take again first case, when A is less than L by 2 and ME was positive. ME was positive. What is happening here? You can see here there are two important points are there. What are those points? Here at this point, suppose this is F point and this is G point. This is F and this is G. Bending moment is changing sign from negative to positive and then positive to negative, right? So there are point of contraflexure. You know that point of contraflexure are those points where bending moment changes sign from positive to negative or negative to positive, right? So where ME was positive, here there are points of contraflexures. Points of contraflexure. What are those points here? F and G. And how to find out these point of contraflexure? We want to find out point of contraflexure. How to find out that? You know that bending moment at F and bending moment at G is equal to 0. Bending moment at F and bending moment at G is 0. You can see here 0, right? So we have an equation for this. This was mx is equal to minus omega x square by 2 plus omega L plus 2a by 2 multiplied by x minus a. In this equation was valid between B to C. From B to C, this was valid from here to here. So we can use this equation. This was valid between B to C. So in this equation, if we put mx equal to 0, we will get a quadratic equation, and solving quadratic equation we will get two values of x, and that will be the points where bending moment is 0, or point of contraflexure where bending moment changes sign, basically, right? So in this equation, suppose the bending moment is changing sign at certain point, because quadratic equation will come. Suppose this is y distance from here, y distance, and another will automatically come, because there will come two values, because it is a quadratic equation. So suppose this is a y distance and we want to find out this y. So put here x is equal to y and equate to 0, right? So what you will get? Suppose we are finding the point where bending moment is 0, changing sign. So we put here, you will get the value of y. I am arbitrarily taken the y. So x now become y plus omega w L plus 2a by 2 y minus a. This is a quadratic equation, and that is equal to 0 at point F and G, right? This equation was valid between B and C. So because these 2 points are lying between B and C, that's why I have taken this equation of B and C, right? And here I have assumed that the point where bending moment changes sign or bending moment is 0 is the distance, having distance y from A, right? So previously it was x1, now it is, I have taken y, right? From here, solving this quadratic equation, you will get two values of y. One is for F and another is for G, because there are 2 points of contraflexures. So what value you will get? Solve it, and you will get y will be equal to L plus 2a. I am writing the final answer only. L plus 2a plus minus under the root L square minus 4a square, L square minus 4a square by 2, L square minus 4a square by 2. So this is the value of y, the points, the distance from the free end, one of the free end, where plus minus means there are 2 points where the bending moment changes the sign or point of contraflexure, right? So distance of point of contraflexure, this is the distance of points of contraflexure from A. This is from one of the free end we are taking from A, right? So by this you can solve all the related topics of this case, overhang beam with UDL.